Welcome back to how to build an advanced trainer with analog version 1.2, or volume, really it's volume 1.2. We started out with 1.0, we did 1.1. Those were all graphics illustrating what we were doing and why we were doing it, and then they were even further supported by the third part in the Basic Electricity Magnetism playlist that talks about backplanes. So anyway, here we are with the third piece of building an advanced PLC trainer with analog. This will be almost entirely video clips of the assembly process. I'll just mention right off the bat, I originally was not planning on doing this, but when I sat down and started building, I thought, you know, it's not that much extra work to set up a camera and, you know, take little clips of what we're doing. Unfortunately, since I'm only building one of these, I only had one chance to get it right. I accidentally hit one of the buttons on the camera that reduced the resolution. I discovered that, but too late. Two clips were small, so maybe I'll put those in, maybe I won't. And then one of them, I hit a color alteration that took out the red and made it bluish. But I discovered that. But again, the work was already done, so I couldn't back up and redo that. So if that's going to annoy you, don't watch this video. But for the most part, it's pretty decent. And remember, there are cases where it won't focus exactly right, or my hand is in the way while I'm soldering, or smoke from the solder. By all means, you can always kind of take the slide bar and slip through here and skip the parts you don't like. What we're going to build is a universal I/O demo unit, or practice unit, training unit. We'll just call it a universal training I/O fixture. And inputs and outputs for PLCs, for programmable automation controllers, programmable logic controllers, for controllers. There's digital inputs, digital outputs, analog inputs, analog outputs. Now you can expand that a little bit further into motion control, instrumentation, etc. In a previous video, I went through the step-by-step procedure to build a real simple piece of training hardware using the Micrologix 1000. As a matter of fact, I have one of those right here. And if you remember, we soldered wires to these switches. We wired a common, soldered a common all the way across, came out through here up to positive, and then we soldered individual conductors to each of the one side that normally open, and brought up these 6 inputs. And then we also brought in 24 volts DC power and ran it up to the power for this controller. It's a 10-point I/O Micrologix 1000 brick. And then we took the 24 volts DC through these red and black conductors over to here. 24 volts we used to power the switches that power the inputs. So this was a real simple piece of training hardware. I sell these on my website mainly for people who don't want to build their own and do not want to use a simulator. So this is strictly digital, 6 digital in, and then you actually use it like this. So you set it on the desk, there's your 6 inputs according to the switches, and there's your 4 outputs. So there are no outputs actually wired here. They would be wired to these terminals here. Instead, you just look at those 4 LEDs as you operate the switches to see if your logic's actually performing correctly. And of course, this was your programming port, DIN connector, and it's the only communications port on this processor. This box is not going to be permanently wired into a particular processor. All we're going to do is bring in 24 volts DC and I see that I have left that one component out of the mix here. Let me grab one of those. Maybe later I can edit out the things I don't like. So this is the 24 volt DC. Well, actually it's just a power connector. I buy these at Radio Shack. You can order them off of the web. And by the way, make sure that when you buy one of these that it's a good mate to the power adapter that you're going to use. This is a 24 volt DC power adapter, and you probably can't read that, but it says output 24 at 1 amp. So this, and it should be snug. I mean, it shouldn't be sloppy in there. It should go in, and gravity shouldn't be able to shake it loose. So of course you need the 24 volt DC power adapter, and you need a power connector to get the 24 volts DC into the system. So remember, we have digital inputs and digital outputs. So for digital inputs, we typically use single pole, single throw toggle switches, and you can see it's a single motion, single pole, well, actually this is a single pole double throw. So right now these two contacts have continuity. It's always on the opposite side of the switch leans. You flip it over there, and then these two. So you could say you have it normally open, normally closed in any position. We just use the center in one of these for each of these switches. So we have 10 switches. Now, most I/O modules are 16 point. So you're probably thinking, well, why doesn't he use 16 switches? Well, if you look at the box that we're going to use, 16 switches would really crowd it, and I wanted to use a box that was readily available. And any more than 10 inputs, that would be a quite convoluted piece of programming. So with 10 switches, you can have start, stop, you can have simulate some sensors, you can do a lot of things. Also remember that if you want to get really clever, you can multiplex these switches, so the position of one switch switches the functionality of these 9 switches to a different set. In other words, you write logic that looks at the very first switch, and if the switch is on, then the other 9 switches do a particular thing. If the switch is off, then they do something else. And you can write that in your program. Remember that it's all bits in memory. Okay, another thing that I'm adding, and I've mentioned it before in some of my videos, is I'm taking normally open push buttons. Because sometimes you just like to push a button and you don't want to actually toggle the switch, you just want to push the button. And so we're going to wire or build these normally open push buttons in parallel with the contacts that we're using on the toggle switch. So if the toggle switch is off and you push the button, then the input goes on. When you let go, the input goes off. So as long as the toggle switch is off, you can use the push button. However, if you want the inputs to stay on, then you just use the toggle switch. So we're going to wire these in parallel. Okay, so those are our digital inputs. For digital outputs, we're going to use LEDs. And I have 5 colors here. I don't know if you can see them all inside of the camera lens or not. Oh, by the way, these are the washers and nuts for these push buttons. These have the washers and nuts still on them. I didn't take them off. So for digital outputs, we're going to use 24 volt DC LEDs. Now, if you know anything about LEDs, you're saying, well, what's a 24 volt LED? They're like 1.2 volts or 9/10 of a volt, depending on the semiconductor material. These all have resistors pre-wired into. The reason I didn't take these out of the package, by the way, is because I have white, red, yellow, green, and blue LEDs. And I want to keep them separate because when I look at the lenses, I can't tell what color they are. You know, I'd have to hook them up to 24 volts DC. So these come pre-assembled with the correct value of resistor to drop the voltage from 24 volts DC down to the small voltage that the LEDs actually require. So for digital outputs, I'm actually going to connect in 10 of these LEDs. Now I have 5 colors, so just for grins, I might use 2 of each. You know, 2 white, 2 blue, 2 green, 2 yellow, 2 red. Now you're not going to want to waste your money like that. I figured these will come in handy for something, and I bought these off of the web, and I think I paid about $6 a pack, and I bought them from somebody in Michigan. Maybe if I get a chance, I'll create a little PowerPoint and animate it and bring it into this presentation that shows a schematic for the whole project, and then maybe I can show links where I bought some of this stuff. But if you go on the web or eBay and type in 24 volt 24 VDC volts DC LED, you'll find these. You'll eventually find them. This particular person probably sells more than just these 5 colors. I don't know. I bought 5. So put these back in here. Now, how these LEDs mount in the box, I'll just pull out a red one here. You also need to order these little plastic bezel mounts, and these basically slide over the LED like that, and then you drop the whole assembly down in the hole on the front of the panel, and these little black plastic bezels snap into a 1/4 inch hole. So that's how you mount your LEDs. Oh, see, that one doesn't want to come back off. I can get it off, but I won't for right now. And I'm going to put these back in the red bag, just so I don't get them confused. So, if you look down here, we've got 10 of those little bezels. We're going to use 10 LEDs. We've got 10 toggle switches, 10 push buttons. That's our digital in and digital outputs. Now to our analog in and analog out. So analog out is very simple. We're going to use these 10 volt, 0 to 10 volt meters. I think I bought these from All Electronics, which is they mail out little catalogs on cheap paper. They got all kinds of electronic gadgets, components that you can buy for hobby projects. So this is 0 to 10 volts. Here's your 2 connectors on the back. That's hold down screws. The real challenge with these, and you'll see in a minute how I did it, is this round area here, I think is about 2 1/8 inch or 2 3/8. I can't remember exactly. But you can see that if you make that hole too big, then you're going to have the hole showing underneath the meter on the front of the panel. So I only made the hole in the panel just big enough to clear this section, which means that this surface here is going to set against the panel face, and there'll be a gap there. You could put in a little piece of foam strip to trim it to make it look better if you like. But these, you shouldn't pay any more than $10 to $15 a piece for these meters. Now, if I'd had time, I would have waited until I got the digital meters. You can buy those for $6 to $10 a piece from China, free shipping, and they are like 0 to 30 volts, 0 to 20 volts, and you would have to cut a square hole in the face of your panel to mount them. Okay, so these are our digital outputs. In other words, from the controller, analog, as the analog outputs vary, the needle will move from 0 to 10 volts. So naturally we're going to use 0 to 10 volts DC for our analog outputs. And you can already see what we have for analog inputs, and those are our potentiometers. Now, you don't have to go as expensive as I did. These are 10-turn potentiometers, and they're 100K, 100,000 ohms of resistance. Now, when you're building input devices for a controller, you want to use very high impedance. You don't want to use low impedance that draws a lot of current from your supply, because it's the voltage that you're sensing, not the current. So these are 100K, and then also I got these vernier locking dials, and there's a little tab there. You probably can't see it behind my fingernail, but you can drill a little hole in your panel and that slips in there so this doesn't move. Or you use this and you lock it down and then that tab fits in like that. But what these are for is it gives you 10 turns, and you can, if you're looking, you can see that for every complete turn here, that moves once. So this would be your most significant digit, and these are your least significant digit. So you can actually have marks that go from 0 to 100. Most significant, you know, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, and then hundreds, 0 through 99, and then this jumps to 1, 0 to 99 jumps to 1, 10 turn pot, and this is a lock. So if you slide that down, then the knob doesn't turn. These aren't very expensive, and they kind of add a little class to your little box. Now, here's something very important. We're using 24 volts DC, but our analog inputs are 10 volts DC. So we have to get rid of 14 volts. So to do that, I assembled some resistors, and by the way, those resistors, they usually come looking something like this. Okay, and you can't read that, but that says 4.7 ohms. Well, that's nothing. But some of them are 470, there's 47K, 470K. You see resistors typically go in 4.7, 3.3, 6.8. They, as far as the actual divisions go. So basically, I took a 100K resistor, and if I put a 100K in series with 100K, I would get 12 volts and 12 volts. So I need to drop a little bit more voltage here. So I took two 64Ks, no, two 68Ks. So I've got 100K, two 68Ks in parallel, gives you 34K, and then I put a 4.7K in series. So if you add that up, 100, 34, and 4.7, you have 38.7K, which means that this will drop a little less than 12 volts, and this will drop a little more than 12 volts. Okay, I'm sorry, 10 volts. This I wanted 14 volts across this and 10 across this, 24 total. So 0 to 24, I wanted 10 volts and 14 volts. This will only actually drop about 13.9 volts, close enough for the folks I hang out with. So unfortunately I didn't take a video of me soldering these together. So basically I took two resistors, twisted the ends, took another resistor, attached it, soldered, and then I took heat shrink tubing. And by the way, there's no polarity. Resistors have no polarity. So there's the two dropping resistors for the potentiometers. Now, if you buy this type of vernier dial, it will come with Allen wrenches, and you need those to lock the shaft down to the potentiometer. So make sure you don't lose that. So here is pretty much all the parts and pieces that you're going to need to build this little project box. I'm trying to think if I've left anything else out. Of course, you need some tie wraps, you need some solder, you need some wire, and if you use color-coded wire, you're ahead of the curve because you don't have to keep track of which wire is connected to what. You just use a color code, and of course, if you buy a cable that has 8 different colors in it and you strip the outer sheath off, you can use the 8 individual conductors. Well, that's only 8 colors. We've got more than 8 things involved here. So I wouldn't go out of your way trying to find a cable with a lot of conductors in it. I would just wire this all up a section at a time with the different colors so you don't get it confused. Now, I didn't say much about this box yet, but this is the largest box that they sell at Radio Shack for projects. And I'm hoping you can see this very clearly. You can see I've drilled out some holes here, and we're not going to put this in the back, but you can see how that fits through there. It's going to fit through the front like such. Okay, but basically the meters come with a little sheet of paper that show you dimensions, critical dimensions. So I basically took a straight edge like this, and I scored lines with my pocket knife across here, so I had the centers for the holes, and you can even see some score marks there. Maybe you can, maybe you can't. That's where originally I was going to drill the hole to try to drop the whole meter down in there, and then finally I realized it was too much hassle. And so I did the same thing for where the potentiometers mount. I used scoring, and we'll turn this around. I don't know if you can see the score lines, and you can see I messed up a little bit, but still close enough for the folks that are going to see this. That's you and I. And so you see I drilled a series of holes, and of course this is plastic. You could do this in metal. Metal's a little bit more difficult to work with, but you can be a little bit more accurate with your drilling. With plastic, if the bit grabs wrong, it tends to walk a little. It tends to grab and pull in one direction. So LED, toggle switch, and push button. So showing you me drilling all these holes in here is absolutely worth it. As a matter of fact, you can see that I didn't get the holes exactly right, so I had to use the drill bit and kind of enlarge it. Well, it doesn't matter because none of this is going to show anyway. The only thing that's going to show that I might not have liked was the score marks. But since this is a practical application, we can live with that. Okay, that's all the parts and pieces. Okay, that's a good stopping point. We've done the lineup, meaning that we've gone through all the components and the labor of drilling holes, marking it up to drill the holes. You know, and at some point I do come to the conclusion, because remember, this is the first one I built. I didn't build one of these and then another one and get it right and then do this video. I sat down to build this because I was headed for the Dominican Republic. I spent time working in a mission down there when I'm not here in the States, and I do PLC professor stuff there. So I'm taking a compact logic, some software with me, and I need an interface to that logic processor in order to develop some labs. So I'm going to build this thing. So I thought, well, I've got time, I'll just hook up a tripod and a camera and do some clips. Well, they didn't all come out perfect. So there's the lineup, going through all the components and one way of laying out the stuff on your project box. So that was volume 1.2. You need to find volume 1.3.